Okay, so today we have Bruno Poggi from Autònoma de Barcelona. He will talk to us about eigenvalue problems and the landscape function. Okay.
Thank you very much, Guillermo, for the invitation to speak at the seminar, and thank you everyone for coming today. I'm very happy to be here. And yes, I want to talk to you about some work that I did last year and around the summer. Well, I finished it around there. So first I want to talk to you about what this landscape function is. So throughout this talk, I'm going to be talking about Schrödinger operators. And for me, what these are these operators minus delta plus v, where v is just a non-negative non-negative function, right, on Rn, say, or on some bounded domain. And here, the gist of well, there's a phenomenon that occurs when the potential V, which I will sometimes refer to as the electric potential, when its values are given in some random ways. Okay, so for example, suppose that your domain where there's a square in R2, and each black dot represents the value of V is equal to 1, and each white square just means V is identically 0. And if these values are given sort of randomly, like say some Bernoulli random potential, then what will happen, interestingly, is that the eigenfunctions for this operator will localize. There will be like these sharp spikes in some part of the domain, right? And this phenomenon is called as Anderson localization. It means the localization of the eigenfunctions induced by the randomness of the potential. So this phenomenon won Anderson the Nobel Prize in Physics in the late 60s, and it has been studied both in physics and mathematics quite heavily. Now, a recent tool that was developed over the last decade, and right now is being studied a lot, is the landscape function of Marcel Filoche-Mayboroda and Filoche-Mayboroda. What this is a function u, which is a solution to the equation minus delta u plus v u equal 1, right? And here, with some boundary conditions, say for the boundary conditions, you can choose them according to the eigenfunctions that you want to study. So if you want to study Dirichlet eigenfunctions, you can choose the boundary conditions to be Dirichlet zero Dirichlet boundary conditions, for instance. So now the gist of this is that the landscape function magically predicts where eigenfunctions will localize. Well, I say magically in the sense that what we have most of the time are very sharp numerical results. So here's some more precise version of this. Suppose you have, again, this is just a picture of what V looks like. Black dots is where it's 1, white dots is where it's 0. Then there is an algorithm that you can do the level sets of the landscape function at a certain value corresponding to the eigenvalue that you're trying to study the eigenfunction of, and this creates this landscape, right, of the domain. And it happens that the eigenfunctions will localize specifically in one of these values. All right, so it's now this, of course, is not like it's just compactly supported in there, because eigenfunctions are not zero open sets. It just you think of it as a numerical result, and even here you can see it's not completely sharp, but there's still a truth in here, because this happens for first eigenfunction and then for second eigenfunction and so on, and it's very accurate. Like, and if you change the randomness, it still works up to say 100 eigenfunction. Then it starts to not work as well, but that's because the energy rises so much that now the eigenfunctions will decouple into several values. So at some point, a single eigenfunction will share its localization in several of the values. For instance, so this was first understood, well, through these numerics and in some physical argument way, but also it's interesting to study mathematically what's going on here. So recent article on this, we sort of mathematically studied this. Is this article of Dogarno, Guy David, Marcel Filoche, David Jerison, and Filoche-Mayboroda, where they prove exponential decay of the eigenfunctions for the Schrödinger operator in terms of a distance that is using the landscape function as a weight. So, and we will see something like this a bit later in the talk. But the point is, there's already some result, although the mathematical result of is not capturing this picture this precisely. So there's still a lot of work to be done in trying to make the mathematical results more precise. Right? And now let me show you another way that there's some magic in here in terms of how well certain certain things are predicted by landscape function. This regards counting eigenvalues. In mathematical physics, it is there is a big project to understand the eigenvalue counting functions and the spectrum more generally of Schrödinger operators, okay, because of a certain physical analog of its meaning. So for that reason, these problems are studied heavily, and I will go into more detail on some literature on the eigenvalue counting problems later. But for now, what I want to show you is that here, like how so well a certain approximation using the landscape function gives you like the real eigenvalue distribution, right? In so precisely in numerical sense, right? So what do we have here? In the black line, you have a Schrödinger operator, right? And in the black line, you are counting the number of eigenvalues at that energy. So you think of E as the eigenvalue, right? And then at that number E, you are counting how many eigenvalues you have below E, right? So there is a result, a deep result from the beginning of the 20th century by Harmonic, where he proved what's now called as Wald's law, which gives you the eigenvalue asymptotics. And it's basically a theorem telling you how the distribution will look like at infinity. Okay? And now what is graphed here in green is what would be that prediction from Hermann Weyl, right? Which is basically a function that looks like this, but here instead of W, you put V, where V is the potential, right? And this thing, the theorem says that it agrees at infinity with the black line. So green line agrees with black line at infinity is the theorem. But what we have here, the theorem says nothing about the beginning of the spectrum, right? Like here, of course, it can be very different. But what we see is that if you just play around and you do not write V in the definition of this approximation, right, for counting eigenvalues, but instead you write 1 over U, so it's a reciprocal of the landscape function, where the landscape function is the solution to this equation that I mentioned before, then this gives you the red line, and you can just see how well in many different models it approximates the eigenvalue counting function. So this thing is this kind of result to this precision is still not understood mathematically, like why it's this precise, although there is some mathematical result on this by Guy David and Fefferman-Phong-Shen from like 2 or 3 years ago. But there's still open question because like this is very precise. So there's even the question of how to quantify how close it is, right? Because it's not perfect either. But anyway, so as you see, this function has these somewhat interesting properties. Now you want to know why it has these properties. And mathematically, a big thing, I think that's doing a lot of work, for instance, in the proofs that we have at the moment for the theorems, is this algebraic identity. This comes about using integration by parts, and just the formula, the solution, the fact that it solves the equation. And then what you can prove is that for any function f with enough smoothness, the energy of the system, which is what here's on the right-hand side, is equal to this conjugated energy. Okay? And now what's important about this is that if this term here is non-negative, so throw it out, and you get this estimate, which we call an uncertainty principle, for reasons that I will say later. But the point of it is that I am giving a bound, I'm giving a lower bound on the energy of the system by a potential energy, by a potential energy, right? But this potential energy is not just V. You could get a trivial result by just putting V, because you could throw out this term and get V here. But the point is that I'm using 1 over U, which is somehow taking in the information also from the gradient in some way, right? And so you can prove this, and this is a very sharp result that is going to give us a lot of the theorems later. So this is one way in which the landscape function, it's magic, right? Like the point is to understand why it's doing all of these nice results. It seems that this is playing a big role. So you can use this estimate along with arguments of small Agmon to prove the exponential decay of eigenfunctions. And that's what they did in the 5-author paper. And then there have also been obtained non-asymptotic bounds on eigenvalue counting function, for instance, recent paper of Guy David, Marcel Filoche, and Filoche-Mayboroda. Now, yes, go ahead.
Which are the conditions upon the potential V?
Oh, yes. So, okay, yeah. Thank you for your question. I am always treating in this talk, sorry, let me put it this way. In this theorem, I have written V to be non-negative. And you eventually, in this talk, I will prove it with L1 log. V non-negative, V is L1 log. And it is non-degenerate. That is, it's not just identically 0. Okay, so this is true in the almost generality. Like basically, you just need that V is L1 log and non-negative. Now, non-negativity is important. But in these results, in these papers, for instance, they have further assumptions. They assume V is L infinity, but that's just to simplify the proof. But you can get even to L1 log.
Okay. Also, in the title of the talk, there is the magnetic.
Yes, this is
the magnetic field there.
Sorry, I will get to this eventually. Okay. But first, I wanted to present it for the Schrödinger operator. Yes, with no magnetic field, because this is how it began. Yes. So now the idea of the landscape function has been extended to other models, right? Not just the Schrödinger operator, the one I have shown, but also to type binding model, which is like a discrete version. And then even it has been done for random M matrices very recently. So it's this idea of taking in an operator and looking at LU equal 1. And somehow in many cases, even very different things, it is giving you a non-trivial information on how on a priori estimation of eigenfunctions. So yeah, I will get to magnetic Schrödinger towards the later end of the talk. I actually already here I mentioned, but so I'll talk about this soon. Now, so here's the thing. As I said, the phenomenon of the exponential decay of eigenfunctions in Anderson localization and all of this has been studied for several decades, but landscape function only come about in 2012 and really only got going in the last few, like 3-4 years. So how does it fit within the classical literature on exponential decay of eigenfunctions? There is already a lot of work on this. So we want to compare, there are other results, and we want to see how, is it sharper than those or is it equivalent? Okay, we will see this. But the problem is that, for instance, in this estimate, this is completely a priori and can in fact, because it's completely a priori, can be useless, for instance, if you have no good property of V, right? So now this is so this is expressed also in this question here. The exponential decay, when I say is expressed in terms of landscape function, what I mean is that you have a weighted distance, which we call the Agmon distance. And this is, you take basically the geodesic on this, on a Riemannian metric with this weight. And then the question is, well, this is a weighted distance. It doesn't need to look like Euclidean distance. But that is what numerical results are saying, at least for random, in the case of randomness. So the question is, how, if at all, is it related to Euclidean distance? And then what conditions do you need to put on V to guarantee that? It cannot be true. We know it cannot be true in the most generality. For instance, if V is 0 outside of a ball, if it is just identically 0 outside of a small ball, then it is not possible, because then this will become bounded, but this can blow up. So what can you put on V to guarantee that, right? And now here's also the magnetic. So I said before that the idea of landscape function have been extended to other models, but extending it to magnetic Schrödinger operator has proved difficult for a while, and the reason is that this is no longer an equation like. You can think of it more like a system. It's vector value, right? It has complex solutions, right? Like the solutions are complex valued functions, and landscape function is a real function. And then, like, well, how could you use that? So if you try to just plug in LU equal 1, where L is this one for the magnetic Schrödinger operator, then it doesn't work. Okay, it doesn't get you anything. So for a while, we were stuck on this kind of question, how you extend to this. And still the question is important because you want to understand how the magnetic field can give you a decay of the eigenfunctions, for instance, right? And here, the A here is a vector function called the magnetic potential, whose curl will be magnetic field. But we'll study magnetic Schrödinger operator a bit later in the talk. Yes?
We are in which is the spatial dimension, because usually there is a difference between 2 and 3 in the definition of the magnetic. You are in dimension 2?
Everything in this talk, well, actually, okay. I can consider it in dimensions 2 and above. So in particular, the main results of this talk are for dimensions 3 and above. Like they are only new in dimensions 3 and above. So yes, the results that I will talk about for magnetic Schrödinger operator will be dimensions 3 and above, because those analogous questions in dimension 2 had already been solved. So yes, so thank you, that's important. And I would say also, remember that in dimension 1, because of a property called gauge invariance of the magnetic Schrödinger operator, it actually doesn't make sense to study it, say on open connected domains. So for that reason, we are, yeah, we don't worry about dimension 1. So we only care dimensions 2 and above. So eventually what we will see is that I can now describe a landscape function for magnetic Schrödinger operator, which works in dimensions 2 and above, and it will give me new results in dimensions 3 and above. But that's a bit of a spoiler. Yes, go ahead.
Out of curiosity,
yeah,
the Agmon distance is a classical character in understanding the decay of the,
yes.
But if I remember the definition, I don't remember now the definition, but I don't remember that the landscape function play a role in the definition of the classical version. Is that equivalent to this?
No, that's an extremely good question. And the thing is that Agmon distance, we can, yeah, because landscape function only was defined like in 2012. 2013. So of course, Agmon distance stuff came from the 70s, 80s. Yeah. So of course, there wasn't anything like this. But the point is that Agmon distance can be defined for any function that verifies an estimate of this form, where instead of 1/u, I would put the square of that function. Okay. So, and that's how Agmon used it. For instance, he used it with v instead of 1/u, which gives you a trivial estimate. But you can also put other functions, and we are going to very soon see one such function called the critical radius function, or the Fefferman-Phong-Shen maximum function, which gives you better results. So yes, classically, landscape function have not been defined. But what I'm saying is that because the landscape function verifies this estimate, then I can consider the Hammond distance with 1 over u, and then it can be proven exponential decay in terms of this Hammond distance. But these are a priori estimates. So then we want to study whether that looks like Euclidean distance in some cases. Okay, so exactly. So yeah, I hope that answers the question for the moment.
Okay.
Yeah, I mean, it will become a bit clearer soon. So before defining the function, I want to say very briefly the conditions that I'm going to be putting on the potential in this talk for some of the theorems. This is a condition of a reverse Holder inequality. So, well, everyone here familiar with Holder's inequality. For instance, this is a easy consequence of it. Now, a function is said to be in a reverse Holder class of exponent p and a negative function if it satisfies a sort of reverse inequality with a constant here for any ball, okay? And this is of course related to the theory that the book can have AP weights, because any AP weight is going to be a reverse Holder weight with some p, not necessarily the same p. Examples of these are the positive polynomials, and then functions of this form, x to the power alpha, where alpha is can even be negative, so you can have singular functions and so on. Okay, some known examples are random Bernoulli potentials. Okay, so these I want to emphasize that landscape function, as it has been conceived for most of the applications in mathematical physics, is studying randomness. But what I'm going to talk about in this talk for a lot of the theorems, I cannot study the randomness. I'm studying something that cannot be random, right? The reverse Holder weights are not random potentials. But a lot of the literature already work with these assumptions, or for instance, with positive polynomials. So it is still a natural thing to study. So we come to the function that I said that has been used with the Hammond distance. One such function, which is the summations critical radius function. In other places, also called Fefferman-Phong-Shen maximal function. And what this is this it is defined in this way. It's reciprocal. You think of it as a radius at the point x, and that is the radius that gives you. Okay, so you think of it heuristically in this way. 1 over m is the radius of the largest ball on which you can consider the Schrödinger operator as a perturbation of the Laplacian in precise quantitative ways. Okay, that's what it's saying. So for example, here's some picture I drew one time and then I have to put it in every talk, right? At the point x, you have 1 over m giving you a ball. This ball has to capture enough of a place where V is really large, okay? And here is why it's interesting from the point of view of Hammond distance. Suppose you take 2 points, x and y, and you take Hammond distance with the weight V, okay, the electric potential. Then if V is at 0 in this wide region, you have no, your Hammond distance is 0, right? It collapses these points because your weight is 0. But the critical radius function of Phong-Shen doesn't collapse them, because at any point it needs to see the parts where V is big. And then it adjusts the radius of the ball so that on these balls, the Schrödinger operator is quantitatively like just a small perturbation of the Laplacian. So this function is primarily interesting because it is suited to work with what is called the Fefferman-Phong uncertainty principle. So if you assume that V is a reverse Holder potential of exponent n over 2 in 3 dimensions or above, then you have this estimate. So you have this lower bound for the energy of the system in terms of a potential energy. And M here is the Shen's critical radius function. So as you see, you can compare this estimate to this estimate. Is the same form, except that this one doesn't have a constant, right? This is somewhat very sharp. In fact, with an extra term, it's an identity. So the fact that it satisfies this estimate means that it is a good candidate for a weight for an unknown distance. And so in the 80s and 90s, and up to the early 2000s, there was a lot of work by Shen to obtain exponential decay of eigenfunctions using this way. But not just, in fact, at the beginning, Shen was not interested in so much the mathematical physical application, but for applications to harmonic analysis. Because in harmonic analysis, you need to, for instance, if you want to prove boundedness of Riesz transforms, then an important thing to get done first is to prove a sufficient decay of the fundamental solution, right, of the integral kernel of the operator. And so what Shen realized is that he can use this idea from mathematical physics, studying exponential decay of eigenfunctions, to bound the fundamental solution of the Schrödinger operator under these assumptions. And so eventually he ended up proving a very sharp result, which is that the fundamental solution to the Schrödinger operator has these upper and lower bounds in terms of an exponential decay, in terms of an unknown distance that has his critical radius function. So it's sharp in this way, although the constants here could be different in the exponent, but still, it is a sharp, we call it somewhat sharp result of exponential decay for fundamental solution, giving you almost precise rate of decay of fundamental solution. And so with this, it is possible then to prove LP boundedness of Riesz transforms associated to the Schrödinger operator. Then beyond this has then been used in the later decade, in 2000, 2010s, and so on, to do extensions of classical harmonic analysis results to a situation related to Schrödinger operator. So considering the extension of Monke-Hall weights. So you can see the work of, for instance, Pascal O'Shea and Besnard-Ben-Ali, work of Shen, and then there's a school in Argentina, Bongianni, Jabores Salinas, Julian Bailey, and many others who work in this intersection with harmonic analysis of this topic that used to be mathematical physics. So you have that, but then also there is application to mathematical physics, which I will mention more literature on this soon. But the point is you can use it to study non-asymptotic bounds on eigenvalue counting function. You can even do this for the heat equation, right? The heat equation with the Schrödinger, instead of Laplacian, you put the Schrödinger operator. Then you can also get exponential decay for the heat kernel. That's done by Katsuhiro Kurata in the 2000. And you have also similar results for the magnetic Schrödinger operator using an analog of the Fefferman-Phong-Shen maximal function. So, as I said, now I have given you two functions which have been used to study Schrödinger operator, and one to study the exponential decay of solutions to Schrödinger operator. And one of them, M of x, is defined to work with the assumption that V is in the reverse order class, and it has all these nice applications to harmonic analysis, but it's not easy, at least a priori, it's not clear what it looks like. It doesn't look so easy to approximate numerically, and I'm not sure if it was ever done before, right? And the other function, U, on the other hand, works in this a priori way, which means it works, you can prove these theorems that work for any potential, but then it's so general that with the further assumptions, you don't know what it really behaves like. And so, and then so you get these numerical results that look really interesting, but you are left with not much theorem saying, giving you actual decay, right? So now the question is, especially because both satisfy the uncertainty principle, they give you a lower bound for the energy of the system. The question is, what is the relationship between these? So we were asking this for a while, but and now it is proven that, okay, the following theorem. Suppose you need 3 dimensions or above. Then assume that V is in a reverse order class with exponent n over 2, and that U is the landscape function on Rn. Okay, and it is possible to define this, and I'll say more about this soon, but the point is that now there exists a constant such that these functions are pointwise equivalent. the pointwise equivalent. 1 over u is pointwise equivalent to m squared. Okay, so this theorem is telling me that anything that was done for m squared, essentially I can recover it for landscape function because they're pointwise equivalent. And in particular, for example, it tells me that the sharp result proven by Song with Shen on the exponential decay of the fundamental solution to the Schrödinger operator can be rephrased in terms of landscape function. For example, a corollary. And so on, there's many corollaries of this I just said, because there was the critical radius function has been used a lot in many results, and now it's like you can just replace it. So you get all corollaries of this form. And now here's another corollary, because the function m, under the assumption that these are reverse order potentials, has a lot of nice properties. And here it means u inherits those properties. So I just brought a few of them that can seem nice. This one is telling you that 1 over u in some way is approximating the potential v under these assumptions in the quantitative way. The next one is a very strong Harmonic inequality, which is if you know, it's a Schrödinger operator, you can try to prove, and you can prove a Harmonic inequality if v is an infinity, for example. But the Harmonic inequality that you get in this way is not as strong as this. This is a stronger Harmonic inequality, which looks almost like it would be like for the Laplacian, but it happens to work for this one in this way. So it's a stronger Harmonic inequality. And then the statement 3 here is telling me how u behaves when it moves far away, and this estimate is easily going to give me that the Armon distance behaves like is controlled by powers of the Euclidean distance. So this here is saying eventually that exponential decay in the Armon distance with the landscape function is equivalent to exponential decay with Euclidean distance. Okay, so this is giving you the first result of how exponential decay in Armon distance with landscape function actually gives you exponential decay with Euclidean distance. Of course, it's important I'm assuming that V is a reverse order class, and random potentials do not verify this assumption. Now, here a quick remark on the actual existence of this landscape function, because how do you guarantee that there is a solution to this? If you're in a bounded domain, that's not a problem because you use last Milgram. Okay, but in unbounded domain, you cannot use last Milgram because the U is not in LP for any P less than infinity, right? So it's not a trivial question. And what we have is a theorem giving you an if and only if statement. On any unbounded domain, the landscape function U with 0 irregular boundary conditions on that domain exists if and only if the Green's function has this decay condition. So this is saying that when you integrate the Green's function for the Schrödinger operator on the whole domain, that it is still a function that is integrable for some Q. Right? So for example, that's not true for the Laplacian. If V is identically 0, it's not true because Laplacian, what is this Green's function? Or say in Rn, its fundamental solution is 1 over x minus y to the power n minus 2. If you try to integrate that, it's always infinity at every point. So not possible. The point of this is asking that V is non-degenerate enough that this is true, and then this is even only if statement with existence of a landscape function. And if that is the case, then u of x is just the integral of the Green's function. You have this, which is not surprising because it's what you would informally write. Yeah. So for proof of this, is just because it's important here. I'm assuming non-negativity of V. In this theorem, V is in L1 log. I can get it all the way to L1 log. V is non-negative, and V is non-degenerate. And it's pretty much just approximation using the maximum principle. It's doing a lot of heavy work for me here. The weak maximum principle. Because actually, for the assumption that V is in L1 log, a strong maximum principle is not true in general. So anyway, that's something. Yeah.
Exists in which space?
Oh, okay, thank you. It exists as a W1 to log solution. It's a weak solution to the equation. It's not in any LP space in general over all of omega. Okay, we have its existence as just a function, which is in W1 to log, which satisfies this equation in the weak sense. And actually, importantly, 1 over u is in L1 log. You can prove this, for instance. And the gradient of 1 over u also exists in some sense. So these things, yeah, this is important. But you don't have any integrability estimate on it. And you cannot have any such estimate because, of course, 1 is not a Lax-Milgren. So, okay. So now we come to the applications, and I come to now I will say what about magnetic Schrödinger operator and these open problems that have existed. And now when I'm going to get to that. How these facts, which seem okay, that's kind of cute. You prove, estimate, yes, 1 over u is like something that was already studied, and you get a bunch of corollaries. But give me something new, right? Like, so here, what I'm going to say now is that these results help us solve conjectures that were outstanding for magnetic Schrödinger operator for several decades. So, eigenvalue counting function. Let me just give a brief overview. Because already I talked about this exactly. Can you hear the shape of a drum? This became a famous article in the 60s by Cash. Basically, the question is this: if you're given a shape in Rn, can you know what it looks like just by knowing the spectrum of the Laplacian on that domain? This is false. It was found out, there's counterexamples, but it is true in many more constrained situations, and it is still being studied. So these kinds of questions about understanding the spectrum of operators also have these applications in geometry and so on. And so, but that is studies by themselves on their own. The question we're going to talk about right now is trying to see what the cardinality of the eigenvalues below some energy looks like. And I said already, there's Wild's law from 1911. The year before this, Hilbert said, no one's going to prove this. It's going to take like a lifetime. And then, like, well, prove this estimate, which is, it came to be known Wild's law. It's a great result. And this is this times this is that green line that we talked about before, right? So you have these eigenvalue asymptotics, but this you can make it even more precise, and that is still an active area research. The more precise question is called Wild's conjecture. You want to know second order terms in their asymptotics. Okay, now that's for the Laplacian. For the Schrödinger operator, you can, however, have a similar idea, and what's being studied is that the eigenvalue counting function for the Schrödinger operator looks like this approximation. It's called the phase space approximation. And under some conditions, this is true that this behaves in this way. But not all conditions, conditions on V, I'm saying. So results I want to say now will not be asymptotic in nature. I want to talk about non-asymptotic results. And what that means is that it would also be true for the bottom of the spectrum, eigenvalues at the beginning of the spectrum, and not just at infinity. So in 1983, Fefferman-Phong proved these non-asymptotic results. So NL lambda here is the eigenvalue counting function of the operator L, which is the Schrödinger operator. And then this until the infinity is a new function defined in this way. You let Qk be a grid of cubes on Rn of silent 1 over square root of lambda. Okay, this is adapted to the value lambda, right? And until the P for any P including infinity is just the number of the cubes where this quantity is smaller than the energy. Okay, smaller than lambda. So this is like LP norm of V over the cube, normalized, right? And you're saying that it is less than this energy. And what they proved, and they proved it for positive polynomials, okay, it was that these up to constants, in the inputs, this function bounds above and below the eigenvalue counting function of the Schrödinger operator. So this immediately had many applications, and we celebrate a result. Shen later extended these bounds to the magnetic Schrödinger operator when n is equal to 2 under some assumptions. So for dimensions 2. Now let me be a bit more specific, and now let's actually study this a bit more in detail. The magnetic Schrödinger operator looks like this. There's a typo, it should be a plus b here. But anyway, this vector function A is called the magnetic potential. Its curl is a magnetic field. You can also define this in dimensions higher than 3. Okay, then it's a matrix. You think of it as a matrix, and given by these values. Right, and more generally, it has a nice topological definition. A is a 1 form, and then B is a closed 2 form. Okay, which is the dA, right? So the exterior derivative of A. So now I write the Shen's extension of the result of Fefferman-Phong for the magnetic Schrödinger operator. And what he proved is that you can bound the eigenvalue counting function of the magnetic Schrödinger operator above and below, again by these adapted counting functions to this grid of cubes. Now this eigenvalue, this function is going to not just take into account the LP norm of V, but also the LP norm of the magnetic field of V. So this is an interesting thing about magnetic Schrödinger operator, which will come up over and over, which this thing that doesn't actually appear in the equation, in the curl of A, is important for the quantitative results of the magnetic Schrödinger operator. And this was already understood for a while, and that's because of the gauge invariance, which is a property. I can talk about that later, but anyway, provided, okay, the assumptions to prove the results, Shen assume that, well, remember 2 dimensions, he assumed that B plus B is in reverse Holder class with exponent p bigger than 1, and that the magnetic field does not change sign. You see, when you're in 2 dimensions, magnetic field is a single function, so it makes sense to put this condition that B doesn't change sign. And he was able to show this in this sort of great generality. Well, great generality in the sense that you're not asking anything more of B and no more smoothness. Okay. Now, what about 3 dimensions and more? Well, in physics, of course, 3 dimensions also very important. But also 3 dimensions and more. He also proved non-asymptotic bounds on the eigenvalue counting function in 3 dimensions and more. But now he has an extra assumption on the magnetic field, which is that its gradient, that is, by this I mean any derivative of B, and then take its absolute value, and all of them have to be controlled by the cube of his critical radius function, adapted to B plus V, without weight. So this assumption, first of all, is hard to verify. It is known to be true for positive polynomials. That is when the magnetic field is a positive polynomial. And that's about it. But already a priori, you can see that it assumes quantitative control on gradients of magnetic field. Whereas in 2 dimensions, this was not needed. And it was, it's like, okay, is it actually needed? But, and again here, M is Shen's critical radius function that I have defined before. And so then in the paper in 98, in Duke, Shen posed the problem to remove the assumption on gradient of B, possibly, generalizing his sign condition of the n equal 2 case. But this didn't seem, it wasn't clear how to do this. Like in 3 dimensions and above, magnetic field is not a function, it is a vector, it is a matrix of functions. What do you mean by putting a sign condition? So it stayed open for a while. And then we have here a similar question that 2 years before that it was published in Communication Mathematical Physics, upper bound, well, upper and lower bound, but here I only write upper bound, for the eigenvalue counting function of a magnetic Schrödinger operator, where now V is allowed to be negative, and that means you can have negative eigenvalues. So he's counting here the number of negative eigenvalues and giving a bound on those. And the result again is that, and it's a similar counting function, The point is, he's still assuming this. He still assumes the same thing on the gradient of magnetic field. And it was conjectured in this paper that, okay, yeah, that looks kind of strong assumption, but some assumption on gradient B seems necessary to prove the result. So we have the two problems, right? So you have the conjecture that some assumption on the gradient of B seems necessary, and the other, and then you have the other problem on the band of non-negative numerical values when B is non-negative, asking to remove this assumption in some way. Now, briefly, why does he assume this? He assumes this in order to be able to prove the Fefferman-Phong-Uncertainty principle. That is exactly this estimate, right? To prove the analog of this for the magnetic Schrödinger operator, he has to assume this. Well, that was the proof method. Okay, otherwise they didn't have a proof of this. So, and without that, you cannot get going. You cannot really prove anything without the uncertainty principle. It's like a main ingredient. So that is an important thing. And then it has appeared also in many other works in the literature related to magnetic Schrödinger operator, works of Shen, Kurata, Ben-Ali, myself, and Filoche-Mayboroda. Now the theorem now is that in 3 dimensions or above, no assumption on the gradient of magnetic field is necessary for the bound of the negative eigenvalues. And then for the other problem, for the problem of 98, for non-negative eigenvalues, you can impose directionality assumptions on the magnetic field, and you can recover the non-asymptotic bounds of Shen from the previous, from this slide, without this assumption, right? Without the gradient assumption on the gradient. Now, why? Why is this true? Okay, sorry. Let me get back to this slide maybe later if we have time. But this is basically just saying what the directionality assumptions are. But the easiest thing to think is that I'm asking that possibly of the rotation, none of the components of the magnetic field change sign. Okay, so for instance, say in 3 dimensions, I would be asking that none of the, in 3 dimensions, magnetic field can be represented as a vector function. I'm asking that none of its components change sign after some rotation, possibly. Geometrically, you can think of it this way. It is equivalent to asking that the range of the magnetic field lies in a 90-degree cone in R3. Okay? In other words, that it's in an orthonormal basis of R3. It contains all the values of the magnetic field. Okay, for example, and then there are other characterizations of what it means in 3 dimensions. So the point is that if I have those assumptions, then I get to do a trick. Okay, and this is a trick that gives me a landscape function for magnetic Schrödinger operator. Also solving that question, right? Which is this: assume that you have this strong favor directionality. By the way, the assumption, the thing I said, the assumption can be weakened considerably. So that's why that one I call strong favor directionality. Now, you are given this magnetic Schrödinger operator. What I'm saying now is consider a different operator, which is a Schrödinger operator with no magnetic field, this L tilde. What I'm doing here is I'm grabbing the magnetic field from this operator, putting an absolute value on it, and then calling this a new operator. This is a Schrödinger operator with electric potential B plus V. Okay, then it has all the results I talked about for landscape function are true for this guy. So you can consider the landscape function for this Schrödinger operator, right? L tilde U equal 1. That is, U is the solution to this equation on your domain, on Rn, for example. The point is, if you have the directionality assumption, if no component of B is changing sign, then in a sense, I can replace this absolute value with just the sum of the components in a precise sense. And then I can get you this uncertainty principle. I am bounding here the energy of the magnetic, of the system of the magnetic Schrödinger operator, lower bound by the this conjugated energy with this U coming from this made up operator L tilde. And now this first term is throwable because it's not negative, and so I have an uncertainty principle. Okay, so this is how I claim like this is a landscape function for magnetic Schrödinger operator. It's like, okay, and now you say, okay, that's nice, but what does this have to do with the problem of Shen? Well, maybe you also already figured out, but the point is, do what I said, and assume now that b plus b is in a reverse order class with exponent n over 2. Then consider the landscape function for this made up operator of tilde. You get this estimate for this uncertainty principle. On the other hand, I already proved that 1 over u is pointwise equivalent to the Fefferman-Phong-Shen function with b plus b as the weight. So this means that in this left-hand side, I can replace 1 over u with m squared x of v. And therefore, I get this estimate, which is the Fefferman-Phong uncertainty principle for the magnetic Schrödinger operator. And from this estimate, then you can redo the proofs of Filoche-Mayboroda, which itself also those are very interesting ideas. Like it's not so trivial, but like once you have this recovered in this way, I have not assumed at any point anything on the gradient of magnetic field. It follows that you can obtain his theorems after you check that everything actually does go through. You can obtain the rest of you can obtain his non-asymptotic balance on the eigenvalue counting function. Okay, and now here's an example that the theorem has content, because you could say, oh, okay, wait, but is there an example of a magnetic field who doesn't have a gradient and for which your results are true, right? So because maybe there isn't, right? And it's not so trivial because you need to make sure, because B is a closed to form, then it needs to satisfy that you take another exterior derivative that it's 0. Yes.
1 minute.
Okay, yeah, this is the lesson slide. And yeah, it is, yeah, so you can get an example. It's not too hard, and it also doesn't change sign with the magnetic field. And yeah, and this, the point is that this example has the reverse order condition that I want, but its gradient doesn't even exist as a locally integrable function. Yeah. And that's that. So thank you for listening. Muchas gracias.
One has questions.
Well, I suppose that for physicists, they control the magnetic field. So you should, the more interesting case for them will be that where the magnetic potential is linear or the magnetic field is constant. So in that case, all those results apply. Is that true?
Yes, exactly. So yes, in particular, when the magnetic field is constant, already yes, and also some Filoche-Mayboroda result apply because it's constant, so its gradient is not 0. But also this result, my result with the landscape function apply as well, because since it's constant, it satisfies the sign assumptions that I was making. And you are right that of course, in the physics community, they are more interested in the case of when B is constant, and in 2 dimensions, for instance, they want to study an effect called the quantum Hall effect, which is when B is constant and then you vary V, okay, the electric potential. The point also here is that even though the main result here about the non-asymptotic balance eigenvalue counting function of the magnetic Schrödinger operator, even though that assumes the reverse order assumption of B plus B, this theorem is not assuming any reverse order assumption. It's completely a priori. And therefore, it also works for the case of random V, and actually even random B, right? Because random magnetic field. This is not studied as much in physics, but in mathematical physics, there is a lot of papers out there studying Anderson localization through randomness of the magnetic field. And so this, for instance, is poised to be used to study that as well, but this is not part of the result in the current talk. Yeah.
Okay. Just to fix the idea, suppose that we have a constant magnetic field, and now about the electric potential, we assume that we have the Newtonian case, or is that under the condition of the theorem. I mean, we have, let's say, in dimension 3 or dimension 2, we have the electric Coulomb.
Right. Yes, with the correct way. I think so. I need to check, but I think so. I need to check, but because I think they verify the reverse order assumption. The exponent in the Newtonian case, you're saying the exponent, the potential looks like 1 over x to the power, which n
minus 2.
Okay, n minus 2.
In the case of dimension 2.
Okay. No, so say in 3 dimensions or above, it works. And then in 1 dimension, in 2 dimensions, I have to check. But in 3 dimensions, yes, they satisfy the reverse order assumption, the Newtonian case. And that's also why this case was interesting to study already, because it includes these cases. It doesn't include the cases of random potentials.
Okay, and now I have also another question out of curiosity. Yeah. At the beginning of your talk, when you describe the landscape function, then you mentioned that the eigenfunction for different eigenvalues are concentrated on those regions.
Yeah.
Is that your statement? I mean that.
Numerical statement. Really,
it's a numerical.
It's not. There is no theorem on this yet. Although already in this paper there is a partial result in kind of showing a quasi orthogonality according to these values. Okay, but like it's not completely this. But what has been observed over and over again, and is being used in physics community in some applications already to LEDs and so on, is this fact that yes, you can generate the values, and then the eigenfunctions will concentrate on these values.
Okay, and look into that picture. Can I make a conjecture about which region corresponds to the first eigenvalue?
Yeah, that's a good point. No, not by looking at this picture.
Okay.
Not by looking at this picture. No, but there is a game that you can play. Where was the game? This in 1 dimension. You can pose the similar result in 1 dimension for the Schrödinger operator, and in 1 dimension you can still write landscape function, and it will happen that when you, of course, in 1 dimension you can graph. Here I haven't graphed B, but in 1 dimension you can graph B along an axis, right? And then you can kind of predict by looking at where the lowest values of U are. Yeah. So in 1 dimension, suppose your V was really random, right? Like it had the points like this and like this. Okay, and then that's V. But then landscape function is gonna be more regularized. It's like a regularized potential, right? So it's gonna have a lot of ups and downs. Okay, so the point is that, for instance, if you wanted to play that game, where will the first eigenfunction localize? It will at the lowest value of U, of 1 over U. So you can also do that. You can also do that in 2 dimensions, but then it's harder because you need to graph in three dimensions, right? And then in 3 dimensions, you need 4-dimensional understanding. So it's not as easy, but yes, the lowest values of 1 over U is where you predict that this will happen. So first eigenfunction localizes at the lowest value. Next eigenfunction gonna localize in the next lowest value, and so on for a bit. But this is not theorem yet. Mathematically, this is just what has been observed numerically.
But it could be a theorem in the case that the potential is nice. It's a Coulomb potential.
Okay.
Not random. In that case, that will happen. That the first eigenfunction is concentrated in the.
It has not been proven in this case either. I don't think so. No. Okay. There is difficulties with the technical aspects of the proofs. That's why even this the fact that the Agmon distance with 1/u is non-trivial. It's like that was open for a while. And then in this rework, I am giving you a situation where it's not trivial, really, when it is looking somehow like a Euclidean distance. But to be fair, I haven't looked at that specific question which you mentioned in too much detail, not myself. Maybe other people have.
Thank you.
No, thank you for your questions.
All right. So let's thank Bruno again for his excellent talk.